Dear students, today we will be discussing about tunable filters. Tunable filters are an important component in the case of WDM, that is wavelength division multiplexing. Let us see tunable optical filters. Tunable optical filters are key components in the case of dense wavelength division multiplexing optical network, that is DWDM. It is a major component in the case of WDM technique. Or the key technologies to make the tunable filters are mainly based on fiber bragg grating, or sometimes it may be based on MEMS, that is micro electromechanical systems. So we are interested only in the fiber bragg grating based devices. So by using these devices we can achieve filtering action in the case of WDM techniques. In the case of MEMS, that is MEMS means micro electromechanical systems based device, we can use these devices for filtering actions. That means that will filters only some type of wavelength. All other wavelengths will be rejected. So in the case of MEMS based device, it consists of two sets of epitaxially grown semiconductor layers. So that layers, in between that layers, there will be a cavity, that is a Fabry-Perot cavity. So mainly here the filtering action is obtained by moving one of the layer with respect to the other layer. That movement is obtained by using the actuator. Due to this movement of one of the layers of the semiconductor, there will be a change in the distance between the cavity mirrors occurs. Due to this distance change, the selection of the wavelength of different frequency will be changed. That means it will select a particular wavelength. That means that wavelength is filtered out. That is the principle behind MEMS technology. Here it is not in the syllabus. So another type of tunable filters, that is based on fiber bragg grating methods. We have discussed about fiber bragg grating in the previous classes. That means the core of the fiber will have different refractive index by irradiating it with UV light of a particular wavelength. That is how we are obtaining fiber grating structure inside a fiber. So that grating structure act as a filter in the case of WDM technique. So how it will be acting as a filter, that we will discuss. In tunable filters, based on the fiber bragg gratings, stretching and relaxation process of the spacing in the fiber grating takes place. You know that there will be a grating structure inside the fiber. That means it will be like in this form. That is in the case of that is like a sawtooth waveform. That has got a sawtooth waveform shape. That means refractive index variations will be like that. And we will be stretch that grating structure. As a result, there will be change in the selection of the wavelength. So usually the grating structure is used for separating different wavelength when we are transmitting a different wavelength through the fiber. That means a particular wavelength will be selected by using the grating structure. In the case of tunable filters also, we will be achieving that selection process or filtering process by changing the spacing between the grating structure. So this results in the stretching and relaxation process in the periodic variations in the refractive index along the core. That means the refractive index will be, in the case of grating, in the case of fiber bragg grating, there will be variations in the refractive index of the fiber core. So when we stretch that, the spacing between this grating structure changes. As a result, corresponding wavelength selection will be changed. That means in the case of, suppose we are using glass fibers is slightly stretchable. If we are stretching it, then there will be a stretching in the grating inside that fiber. That means usually grating will be inside the core of the fiber. When we are stretching the fiber, there will be stretch in the grating structure inside the fiber. As a result, the spacing of the index perturbations and the refractive index will change. When we stretch that fiber, the grating structure changes. As a result, the periodic changes in the refractive index also changes. And this process induces a change in the bragg wavelength, thereby changing the center wavelength of the filter. So before stretching, let us see the equations. Before stretching, the center wavelength of the fiber bragg grating filter is lambda c is equal to n effective into lambda, where n effective is the effective refractive index of the fiber contained in the grating structure, and lambda is the period of the index variations of the grating. So before stretching, the equation was like this. So when we are stretching or when we are elongating the fiber grating by a distance delta lambda, then the corresponding change in the center frequency will be delta lambda c will be equal to 2n into delta lambda. So how we can stretch that fiber? For stretching the fiber, we are using three methods, that is thermomechanical methods, piezoelectric methods and stepper motor methods. Let us see, in the case of thermomechanical methods, there will be by using the temperature variations, we are changing the length of the grating structure. So in the case of thermomechanical methods, there will be a bimetal differential expansion element, and this metal changes its shape with the temperature. So let us see the figure. You can see here that usually this is optical fiber cable, and that cable, inside that cable there will be a grating structure. That is not shown here. Core contains the grating structure. That means a periodic variations in the core refractive index will be there in that fiber. So this will be attached to this setup. That means there will be a bimetal structure, that is this is one metal and this is another metal, and this metal has a property that is it has got a high expansion property and this is low expansion property. When we are providing heat to this structure, the high expansion metal will expand. As a result, the fiber connected to this setup will also expand. That means the spacing between the grating structure will be changed. So figure below shows the structure. High expansion bar changes its length more with the temperature than the low expansion frame. This introduces a length variations in the fiber grating. So the corresponding wavelength selection will be changed. That means this is a tuning process. So this fiber grating acts as a tunable filter. Similarly, there will be using another method, that is piezoelectric methods. And in the case of piezoelectric occurs, that is piezoelectric method, there uses a material that changes its length when a voltage is applied. You can see here that electric voltage is applied, and this voltage will be, this is a piezoelectric stack, and based on the voltage its length will be changed. That means there will be some vibrations will be produced. Based on that, this will expand, this fiber will expand. As a result, the spacing of the grating will be increased. So the corresponding wavelength chosen by this structure will be changed. That means it will be tuned for a particular frequency based on the voltage applied here. Okay. Next structure is a stepper motor methods. That means here we are using a stepper motor, that is we are electrically controlling this optical fiber grating by using a stepper motor method. So stepper motor method changes the length of the fiber grating by pulling or relaxing one end of the structure. Here you can see that based on the electrical supply given here, the stepper motor may be pull it to one side or it may be pull it to this side. As a result, when it is pulling to this side, the grating spacing will be increased. When pulling is to this side, grating will be spacing of the grating will be reduced. Based on that, the wavelength selector will be changed. So we are tuning this optical fiber grating by using the stepper motor. That means it will be tuned for a particular wavelength by using this structure. So this is all about the tunable optical filters. Actually we are using fiber bragg grating structure to obtain the tunable filters in the case of WDM techniques. So it will be also an important component in the case of WDM or dense WDM structure. Here there is a comparison performance parameter of the tunable optical fiber filter. We are using different parameters such as tuning range, channel selectivity, bandwidth, insertion loss, polarization dependent loss, tuning speed and tuning voltage. Usually the tuning range will be in between 14 nanometer typical, that is a typical value, and the channel selectivity is 150 and 25 gigahertz frequency, and bandwidth is less than 0.2 nanometer. That means a particular wavelength is chosen. That means bandwidth is smaller. That means it will precisely select a single frequency. That is why bandwidth is very less. And next is the insertion loss. Insertion loss is less than 3 dB across tuning range, and polarization dependent loss is less than 0.2 dB. And the tuning speed will be, it depends upon the technology dependent. That means we are using different methods for changing the fiber bragg grating length. So based on that, tuning speed will be different, and tuning voltage is 12 to 40 volt. So that's all about this topic. Thank you.